Welcome to our professional training event. I see some familiar faces, so who's been here before? Welcome, we appreciate you coming back. And who's here for the first time? Oh, thanks, you got a nice combination of people. So I thank you guys for coming. We're going to have an incredible day today.
Okay. So we reviewed when we left for lunch. We're going to move into now what are the genetic mutations specifically. So a genetic mutation, or an SNP, which they call a SNP, so you can have a snippet or a SNP. The gene mutation is a permanent alteration in the DNA sequence that makes up a gene, such as the sequence difference that is found in most people. Mutations range in size. They can affect anywhere from a single DNA building block to a large segment of the chromosome that includes multiple genes. So it can be one, it can be several. These are acquired and they're hereditary. So when I say acquired, there's usually something that'll turn on this snippet or mutate it, right? Like a toxin. And toxins in our world can be thoughts, foods, environmental toxins, chemicals, things that can alter the DNA. So what's the big deal? All right, so to function correctly, and I looked at this little thing. Did you guys catch a spelling error? Look at me being a spelling junkie. So it's dude, you are, yeah, okay, so he can't talk and the other guy doesn't understand him, so that's okay. But to function correctly, each cell depends on thousands of proteins to do the job. Sometimes gene mutations prevent one or more of these proteins from working. So remember how I said the MTHFR gene codes the enzymes that actually build the proteins that talk to the body and tell them to do things. So when this happens, they're changing the gene's instructions for making the protein. They're changing the code of what actually should be done to what actually is happening. So a mutation can cause the protein to malfunction or just be missing completely. So your single nucleotide polymorphism just basically means that along this little DNA chain here, one of the SNPs, one little single nucleotide polymorphism can be altered. And that's all it takes to change the health of people. So here it is. This is a single nucleotide polymorphism called what we call C677T or 677T SNP. And as you can see, this is the MTHFR. And this is a regular gene. So you can see how they're different. And that's all it took, was one little snippet. All right, so on your thing you can draw a bicycle because this is going to help you see where all these vitamins, you should have a blank piece of paper or a blank square. Okay, so we're going to walk around these wheels and fill in some of the things that you can take for particular genome mutations. Now again, I'm going to specify that this is very, very individualized. You can't just give generic protocols to people that are, compound heterozygous, or it's all going to be very different. You don't know what stress their life is under. You don't know how they live their life. You don't know what food, what kind of chemical toxicities that we have. So even with our friend here who's been sharing, which we appreciate you letting me use you as an example over and over again, she had told me that she got exposed to some mold, which made her condition worse. So if I wouldn't know that as a practitioner, I wouldn't know how to help. Okay? So when we draw this bicycle and we fill this in, as we move along with our supplements and our protocols, you're welcome to come up and take a picture of the board. I have all the methyl donors, I have the methyl blockers, I have the methyl burners for our overmethylators. And I basically have the products in here that you'd want to utilize with certain genome mutations. When you have MTHFR, on your next thing, it's like drawing a bicycle with your eyes closed. So if you close your eyes and you draw that same bicycle, that's a prompt to do it. You have to do it. You have to participate. Blocking. And be like, selfie. No, I'm just kidding. When you see that bike, what happens is the instructions, the ride is a little bit bumpier, right? Things aren't communicating. Things aren't rolling as nicely as they would. So MTHFR gene provides those instructions, which plays a role in processing amino acids. Methylene tetrahydrofolate reductase is an important chemical for reaction involving the vitamin cycle, that's this side, Okay, specifically the enzyme converts the molecule methylene tetrahydrofolate to the molecule methyl tetrahydrofolate, which is your MTHFR mutation. When that happens, it can't do that. The process converts the amino acid homocysteine, which is right here, okay, to another amino acid, which it can recycle up, or it can recycle down and become glutathione, which I forgot my E. So if you took a picture of the board before I corrected this, you have the wrong spelling on glutathione. Any questions on how that works? Okay, let's get into some mutations. So there are two main MTHFR mutations that we focus on. And when I say we focus on, there's 50 variants of these. Okay, so there's 50 different mutations or SNPs that can occur within the MTHFR methylation cycle. That's a lot. Right now, we know a lot about 2. As we get better, we'll probably know a lot about a lot more. Okay? These mutations are called polymorphisms, so that's where the SNP comes from. And they're referred to as 677T and 1298C. Mutations can occur on different locations. They can come from one or both parents. Okay? And you have an increased risk of health problems when you have 2 increases much more. So if you have 2, so if you have like a 677T and a 677T passed down, or 129HC and 129HC passed down. When you have 2, you're going to have more. When you have heterozygous, which means 2 different of these mutations, which is what she was sharing, she's 677T and 129HC, these are chronic. This is probably the worst one that you can have. Okay? So you have 2 polymorphisms on the 677 site. So let's go back because this is what that means. So right here, this is 1. She has both. So both sides. Does that make sense? So if she was just a 677T, she would be just this, but she's TT. Okay? She's what we call like, oh, that client. Yeah, she's tough. So we can work with them. Okay, so the MTHFR gene can change the way some people metabolize and convert important nutrients. We obviously know that. It can alter neurotransmitters. It can alter hormone levels. It can affect health parameters, including cholesterol, brain function, digestion, endocrine. Everything that you can think of can fall into these categories. So this basically, you can have 2 different ways. It can alter the shape of the enzyme, or it can alter the function. So it either doesn't fit in the puzzle, or if it fits in the puzzle, it's giving the wrong directions. All right, so research indicates that 45% of people have some sort of MTHFR mutation. 45% are right here. They have some sort of mutation. This is the inability or the decreased ability to turn folic acid to folate, which starts this cycle. And dozens of health conditions result. Okay? So again, 50 known variations, 2 primary that we're going to focus on. All right, so when we're looking at the bicycle, right, so we have one that has 2 good wheels. And I like to say this is a bicycle. So this is kind of like your back pedal. It's kind of like pushing and fueling. And then this is your direction of where you're going. It's the front of the bike. It's steering. So although you're fueling from here, you're directing from here. But this lack of fuel or lack of nutrients or lack of coating will throw you in a whole different direction. So you can have lots of different bicycles. So decreased methylation equals decrease in methyl bodies and a wrong messaging of getting through. All right. Anybody remember the Punnett squares? Do you remember these when they're, oh, we are these in the 4th grade. Here we are back in 4th grade again. Right? You have blue eyes and I have brown eyes, and then our kids are going to have blue and brown eyes. So in a very layman's term, we can kind of figure how this genome mutation is going to affect society. I'm not a geneticist. This is not how they do it. This is how Tracy does it for effect. Okay? So if you have somebody with blue eyes, they've carried 2 recessive traits and 2 dominant. Okay? So obviously they get married and they have 4 kids that carry a recessive blue trait, or called allele. That person goes and gets married to somebody that also carries a recessive, and all of a sudden they have a baby with blue eyes, baby with dark eyes, and 2 recessive here. Now the dominant's going to be the expressive, right? You're going to express brown. So when Eric and I got married, he has green eyes, I have brown eyes. Both of our kids have blue eyes. So I don't know whose they are. They brought him back in the room. I'm like, yeah, sure? Aaron? Okay. I was like, this kid's it's really, really pale white, blue eyes and blonde hair. I was like, have you seen me? Like, I'm not, So genes can be funny, but in theory, that's what's happening. So you have a carrier father, what we call heterozygous. He's carrying either the 677T or the 129, and a carrier mother. They come together, and their chance of having children that are carriers are here. They'll have two carriers and one homozygous, one that has two genes the same. Okay, and then they go and they get married. Now you have this parent. So say father carried 129HC, mom carries 677T. They get married, and here you are, 129,677, heterozygous compound expressive, which means you're sick all the time. You don't know why. You have every ism, ate, orifice, everything you think of, and nobody can figure out what's wrong with you. And so this is what's happening to our population, and it's growing. So now this person can marry a completely healthy person with no mutations whatsoever, and they're going to have children that are now carriers of both. And so it just keeps going, and this is basically what's happening.
But the carriers of both are still going to have some.
If you're 129.8 carrier with no SMP on your other side, you have no symptoms. Your heterozygous 129s, you have no symptoms at all. So you don't even know. And then you go marry a perfect healthy person or somebody that might be carrying a 129, and all of a sudden, now one of your kids is 129 homozygous. And you never even knew because you weren't symptomatic. Now 677T, we're going to find out, gets a lot of attention because even if you're just a carrier of him, you're symptomatic. So that gets a lot more focus because people are sick and they're like, what do I have? And they're like, it's a genome mutation. So the two most problematic mutations that occur are 677T and 129, and it denotes placement of the mutation on the gene. So it's just like a map. This is where that lives on the gene. Homozygous, the same gene passed from both parents. So either 677T, 677T, one from mom, one from dad, or 129.8, 129.8 from mom and dad. That's homozygous. Heterozygous is when one is passed and the other gene is different. This can be no SNP, or it can be the other one, which is known as compound heterozygous. So homozygous means same. So either nothing, no SMP, or 677, 677. Heterozygous means one and a different gene. And then when you're compound heterozygous, that means you're 677T and 129.8C, which means both of these coming together are what are known as chronic disease. Okay? It's not a death sentence. It just means you now know you need more. You need more folate. You need more glutathione. You need more NAC. You need more B12. You need more. You're special. So I never give that sentence to my clients where I'm like, this comes back and I'm like, oh my God, don't do that. You lose customers, one, and number two, they're like this and they're not hearing you anymore. What I say is, you're special. Now we know what's wrong. Okay. So now that we know what's wrong, we can develop a special plan for you, and isn't it awesome to have some answers? Okay? Questions here on what defines homozygous and heterozygous? All right. How many people have no SMP? I laid a paper on your desk. It looks like this. If you are a no SMP, which means you have no genome mutations, it'll say no SMP, no SMP. Okay, stand up if you're good, if you're healthy. So these people right here have no genetic mutation at all, but still have a methylation issue. They still aren't good methylators because no one's a good methylator, right? If we all have some sort of leaky gut and we all can't, process folic acid, we have a methylation issue because we're all kind of tired. We don't sleep well. We're on our iPhones destroying our pineal gland because we love Facebook, right? So you can thank Facebook for destroying your methylation. Okay, so this is half the population that has nothing wrong with them, no genome mutation, but still can't methylate well. Okay? Your reduction in methylation is about 20%. You're not great, but you're still doing well. Okay, you guys can sit. How many people have a paper that says 677T and no SNP? So it'd say 677, no SNP. Does anybody have that paper? Flip it over. Cheat. Look at your neighbors. Okay. Does anybody have 129.8C and no SNP on their paper? Okay, stand up. Now these are your heterozygous. This is heterozygous too, right? Because it's different. So if we go back, if you have 677T and then your other little allele over here is fine, that means you're heterozygous. So they just happen to be 129.8. You guys have no idea that there's something wrong. You have no symptoms. You feel fine, right? But you have a genome mutation that you don't know. Okay? You guys can have a seat. How many people have a double 677T? Boom, boom. Okay, stand up. All right, so you are what's called homozygous. You have two of the same, but you're symptomatic. Now it's heart disease, cholesterol issues, blood pressure, coronary artery disease. That's what we're happening with high homocysteine levels in the blood. And you guys get a lot of attention because if somebody was this, you're still symptomatic. You're still expressive. You're still expressing the same thing, so you kind of know. These guys I consider dangerous because you have no idea. You have no idea if something's wrong. All right, go ahead and sit. Does anybody have a double 1298? Okay, so now you're symptomatic because you have two of the same. So although when you're heterozygous, when you just had one, okay, you didn't have any symptoms. But now when you meet the other one and you're homozygous, now you're sick. This is where your sugar diseases come from, right? This is where some of your neurological issues come from. Diseases like ALS, MS. This is where they're tracing them to. Okay, go ahead and see. All right, so you guys know there's something wrong. You're not quite sure what it is. Who's my heterozygous compound? 677129. How many of those do I have? All right. You guys, it's okay if you, good. You are really sick. You're sick. You have everything that they express and everything that they express in a homozygous. So you could have it all. You could have mood disorders, neurologic disorders, sugar issues, heart disease, anything. And you can't detoxify, and you're super, super sensitive to supplementation. So when we try to supplement you, you go into what's called overmethylation. And then we calm you down. And then you go into immune system response jacks up. So you're all over the place. So getting control of this one is a little bit more difficult. Okay? So everybody sit. All right, so what I want you to do is flip over your PowerPoint, mark your page wherever you are, and just turn it over so I'm not going to lose your page, but go to the last page right here where you have a little bit of space on the back. Then you can't play. No, I'm just kidding. I have paper for my diligent note takers that need extra paper. We're going to draw a Punnett square. You're going to get married to the person next to you. You're married. You two get married. You're married. Hang on. You guys aren't allowed to get married again. You're going to marry her. You're going to marry her right here. Okay? You two are married. You two are married. You're not allowed to marry again. You two are married.
I'm not allowed to marry again.
You're going to marry Rashid. Okay. You two are married and you two are married. Okay. So when we do this little Punnett square, I just want you guys to realize how fast this is going to be. Did everybody, I'm just going to draw down here, okay? So, how many people, so Heather, I'm going to use you and Tammy. Tammy, what is your paper allele say? Like I can see that. Read. So this is Tammy at the top.
677.
So she's a 677T and a 677T, right? And I'm going to draw a line down like this and a line over. And then Heather, what are you?
677T.
Uh-huh.
1298.
And now she's 1298C. And so I'm going to put this in this little Punnett square because I want to see what the probability of children are, right? So I know I'm going to have one child that's a double 677T. And then I'm going to have another one that's a 677T. And then I'm going to have one that's a heterozygous 677T with a 1298. And then I'm going to have one that's a 677 with a 1298. So now I have 2 homozygous and 2 heterozygous compound expressives. All my kids have something. And this is what's happening. So I want you guys to draw out, you guys don't have to do it, I kind of spoiled your game. Sorry, do a different one. You can draw out together what your children probability would be, just to see, which is interesting because you have no SMPs. This guy's completely healthy and you're completely healthy. So you're going to have healthy kids. So you guys stay together because your kids are going to be healthy. So obviously this is not how genetics really work, but it just is going to show you how we can break this down. So Micah, what was your alleles? Yep, on there, yeah. Do you know yours truly? Just give me your fake one. All right, so Micah, is it CAH, right? Okay. So he was no SNP. And then what were yours?
1298C on both.
1298. Oops, I don't want to put that there. So she had 1298, 1298. So although Micah right here had no genetic mutations at all, he was perfectly healthy. They got married and had kids that are now all carriers, potentially, of the 1298C and the no SNP. So all 4 of their kids are now going to carry this genome, this mutation. So when they're up here, though, we know that 1298C doesn't really feel anything, right? They're not symptomatic. So they probably won't even notice or think about it or anything. Right, so now, right.
They go marry somebody else who's got something else.
Exactly. So now on the second generation down, she has a 1298, and we'll just put an X for no SNP. And then they may meet somebody that's a 677T and a healthy allele, and they get married, and they might have one heterozygous, right? They have a 677 here and a 129. They have a 677T and an X. They have an X and a 1298, and they have an X and an X. So this kid has no genome mutations. This kid may have a genome mutation but doesn't know it because he doesn't feel anything. This one is a 677 and a 129. He feels everything, it's probably the worst one. And this kid is a 677T and a no SNP. He's symptomatic, but they're not sure what's wrong. So you might have 2 kids that are perfectly healthy and 2 kids that have these genome mutations. You give them all the same vaccination regimen, and boom, 2 kids have autism and 2 aren't.